Section 3.3, Measuring Variation. In Section 3.1, we looked at ways of using the mean, the median, and the mode to make a calculation to try and measure the center of a data set. In Section 3.2, when we did box plots, we started to get some sense of how spread out data sets were through the graphs we were making. Now in this section, we're going to learn how to make calculations that get a sense of measuring that variation or dispersion or spread that exists in our data sets. So we're going to start off looking at two data sets. Data set 1 has the numbers 70, 77, 80, 86, and 92. And data set 2 is 59, 70, 80, 97, and 99. And just to give context to this, we're going to consider those to be test scores. So let's look at this chart where we're going to try and do our old measures of center, the mean, median, and mode. And I want to show you why that's kind of not enough for this data set, or these two data sets. So we'll start off with the mean. So I'll do some scratch work. Actually, it's pretty short. We'll just go ahead and do that on the calculator real quick. For data set 1, we'll add up those numbers. We get 405, and then there's 5 numbers, so we'll divide that by 5, and we get 81. So I would say for data set 1, we're getting a mean of 81. And I'm using the mu that we learned in the last section for the population mean, which is a little odd here, but it means I'm basically considering this to be, this class only has 5 students in it, so we have everybody. And then we're going to look at the other class and do the same thing. So we add up those numbers, which are definitely different numbers, but you'll see add up to 405 just like they did in data set 1. So when we divide by 5 to get our average or our mean, we still end up with 81. So we have a mean of 81 in both data sets, so both of those measures of center are coming out the same. And yet when you look at this data set, I think you would agree that the two are definitely different. So what about if you look at the median? Well, this one's a little easier to do because the data sets are already in order. There's only 5 pieces of data, so the middle number in both data sets would be the 80s. So the median for data set 1 would be 80, and the median for data set 2 would also be 80. And the mode's also fast. It's not very interesting, but it's fast. There is no repeats in either data set, and that's what we're looking for the mode. So for both of these data sets, I would say that there is no mode. So if we were trying to compare these two data sets just by looking at the measures of center, then it looks like we would conclude that these data sets are not different at all. And yet you look at the data sets, they definitely are different. If you thought of them as test scores, everybody in class 1 passed that test, but there was somebody in class 2 that got a 59 and failed that test. So they're definitely different. There's 2 A's in data set 2, but only 1 in data set 1. So they're different, but they're not different in mean, median, or mode. They're not different in measures of center. So if we want to see the difference start to show up in our calculations, we need to start calculating measures of dispersion. So the first one that we can do is nice and simple. It's called the range. We use a capital R for that, and the range is just the largest value minus the smallest value. So let's do that on the side over here. The range for data set 1 would be the largest value, 92, minus the smallest one of 70. So it looks like our range for data set 1 would be 22. And then if we did the same thing for data set 2, we take the largest value of 99 and subtract the smallest value of 59, and we get the range for that data set is 40. So now we finally have something with the range that's showing us that these data sets aren't the same, and it's saying that they're spread out more, that the distance from the far left to the far right, or from the smallest to the largest, is about twice as big with data set 2. The drawback of the range is the same as what's good about it. What's nice about it is it's fast and easy because it only uses 2 points. The drawback is that it does not use all of the data, and if you're really trying to decide which data set is more spread out, just looking at 2 values might not be enough. Let me just show you a quick illustration of that. Suppose we had 2 data sets, a data set 1 and a data set 2, Doesn't matter too much. I guess I'll do 1 up top and 2 on the bottom. And just suppose these were numbered with the same scale, and that data set 1 kind of looked like this, and data set 2 looked something like this, with a value over here. So which one of these kind of feels more spread out? To me, it seems like data set 1 is more spread out. None of the data is really close to each other. There's no real clusters anywhere. And data set 2 seems to be the one that's less spread out, with almost everything piled in one spot. It just happens to have one value kind of off on its own over here. But if you were to calculate the range, the distance from this largest one to the smallest over here is bigger than over here on data set 1. And so I think that just using those two values, we're missing what's going on in the middle, and this cluster right here, we don't notice that. So if we want to start getting a more overall sense of how spread out a data set is, we can't use the range. The range is fine to get a quick idea, but if you really want to dig deeper, you're going to want to look at something like the population standard deviation. So the deviation from the mean is defined to be the directed distance from the mean. You take the difference or subtraction of every data value x minus the mean, and that gives you how far away they are. Sometimes this will come out negative, sometimes positive, depending on whether our original data was on the left or the right, and that's why it's referred to as a directed distance. And we'll see that come up as we look through this data set. So I'm just going to go ahead and walk you through how to build this, and then we'll write the formulas down afterwards. If you're trying to find this thing called the population standard deviation, then what you want to do is start out finding the deviation for all of your x values. We're working with data set 1 here, and for both these data sets we had a mean of 81. So when we go to do our deviations, we're just taking each x value and subtracting that 81. So this first line, what I would be doing is the x, which is 70, minus the mean, which is 81, and I'd get negative 11 there, and that would go in this first spot. So I don't want to show all that work in the table, it gets a little messy, but there's the first one. So that gave us this number, and then we keep going like that. So 77 minus 81, I'll show one more over here on the side. We get negative 4, so that's this deviation. And then just keep going, I'll do the rest in my head. So 80 minus 81 would be negative 1. 86 minus 81 would be 5. And then the last one, I guess I'll write that down too. You have 92 minus 81, and that would be 11. So we see a little bit of this directed distance idea coming up, because 70 is 11 units to the left of the mean, and so we're getting a deviation of negative 11, whereas 92 is 11 units to the right of the mean, and that's coming out as positive. So whenever your x values to the left, you get a negative deviation. Whenever your x values are to the right, you get a positive. So this thing is called the standard deviation that we're trying to find. So here's our deviations. And so if you thought, well, what do they mean by standard? Maybe they mean typical. Maybe they mean average. And if you thought they meant average deviation, then you'd probably want to add these up and divide by 5. So if we were to go ahead and do that and start adding these up, we get negative 11 minus 1 and a negative 1. That's negative 16. And then we have 5 plus 11. That's a positive 16. So if we added all that up, we would get a 0. And it turns out that's not a coincidence that we're getting 0 here. That happens for every data set. One of the things we mentioned in section 3.1 is that the average is a balancing point for the data set, and it achieves that balance by balancing the total distances on the left right here with the total distances on the right. So this is going to happen for every single data set, and if all data sets do the same thing here, then we're not going to be able to see differences in spread if we are adding these up and having the negatives and positives cancel out. So there's a couple things that we could do. Our goal here is to get rid of the negatives before we add them up. One way to do that would be to just get rid of the negatives, but it turns out that mathematically it turns out to be a little bit better for the calculations if we square to get rid of those negatives. So if we take that first deviation, negative 11, and we square that, we would get 121, and that would be my first entry here in the x minus mu squared column, and then I would keep doing that. So the next deviation, negative 4, I would square that and get 16. Negative 1 squared would be 1. 5 squared would be 25, and then finally I square this last deviation of 11, and just like the negative 11, when I square it, the negative doesn't matter anymore, and I get 121. So now all of those are positive, and I want to know what the total is. So I'll add those up real quick on the calculator. So 121 plus 16 plus 1 plus 25 plus 121, and we get 284 for our total. So 284. So that's the sum of those deviations, some of the squared deviations actually. And now we could go back to what we were starting off saying we were trying to do, get a standard deviation or maybe like an average deviation. Well, we've just added 5 numbers together, so it might seem reasonable to take that 284, since that came from adding 5 numbers, to then go ahead and divide it by 5. And if we take our last answer, 284, divide that by 5, we get 56.8. And I suppose you could say this was the average of our squared deviations. But when I think of standard deviation, I think of maybe typical deviation or typical distance away from the mean. And if we look at how far away from the mean these numbers were, they were 11 away, 4 away, 1 away, 5 away, 11 away. None of them were anything close to 56.8 away. So this answer is coming out way too big. And why is that? It's because of the squaring. The squaring did a good thing for us. It got rid of the negatives, but it did a bad thing as well. It made these numbers all a lot bigger. So what we're going to do to get rid of this kind of growth we got is do the opposite of that squaring, and we're going to end this process by taking a square root. So we're going to take the square root of that 56.8. This is going to be our population standard deviation. The symbol for that is the lowercase Greek letter sigma, so I'll put that in there. And it's going to be the square root of 56.8, which I'm sure will be messy, so I'll put an approximately equal on that, and let's see how that turns out. We have the square root of 56.8, or our 56.8 sitting there. Now we want the square root of that. And the square root of 56.8, I'm going to round that to 7.536, and I'll write one more digit, and it's a 5, but it's followed by a 7, so I'll write a 6 for that. And then I just want to kind of show you that does make sense as a typical distance away from the mean. Now, instead of having a number that's way bigger than all the distances, at about 7.5 we have 2 values, 70 and 92, that were further away from the mean than that, and then 3 values that were closer to the mean than that. And if we're trying to get some sort of typical distance, we'd like to see it have that trait, that there's some numbers that are further away from the mean than that, and there's other ones that are closer. So that's your first look at calculating population standard deviation. I'll go ahead and show you the formula here as well. So when you're doing the population standard deviation, you use the lowercase Greek letter sigma to represent that, and you take the square root of the sum of the squares of your deviations divided by the size of your population. So that looks pretty messy, and the best way to handle this messier formula is to do it in pieces. So we found our mean, and then we subtracted everything, then we squared, we added, we divided, and finally we took the square root. And we'll look at that process again on the next page, so we'll get some more practice with it. And then one other definition is the population variance. That would be the sigma squared is called the variance. It's the same thing, it just doesn't have the square root on it. So if you thought about that in terms of this example, you could say that the variance was 56.8. We don't use the variance much in a intro stat class. We focus more on the standard deviation, but this is also an important term in statistics, so it's at least good to be aware of what that is. Alright, we're continuing on with section 3.2 on the standard deviation, and I just want to make a note here. If it's really the job of the standard deviation to measure how spread out a data set is, then the more variation there is in a data set, you would think the larger its standard deviation would be. And we're going to kind of test that theory out here by looking at the standard deviation for our other data set 2. So if we were to go back and look at the data sets from the previous page again and compare data set 1 to 2, we know from the range that it seems like the distance from one end to the other is smaller for data set 1, so we would kind of tend to think that data set's more spread out. But even when you look in the middle, 70 and 97 are further away from each other than the 77 and 86. So I think we do have more spread in data set 2. So I would expect that when we calculate the standard deviation for data set 2, it's going to come out to be larger than data set 1, because it just looks like that data set's a little bit more spread out to me. So to this question of how do you think the population standard deviation for set 2 compares to set 1, I expect it to be larger. And now we're just going to run through and calculate the standard deviation for data set 2 and kind of confirm my suspicion there, I hope. So let's go ahead and do that process. So you might remember that both data set 1 and 2 had the same mean of 81. So my first number in this chart would be 59 minus 81, and I believe that's negative 22. So I'll go ahead and fill that in. And then continuing on with that kind of calculation, 70 minus 81 would be negative 11, 80 minus 81 would be negative 1, 97 minus 81 would be 16, and our last number, 99 minus 81, that looks like that would be an 18. And we don't really need to add this number up because we're not going to use it, but if we wanted to confirm our work, we could do that. The 16 plus 18 is 34. Negative 22 and negative 11 would be negative 33, and another negative 1 would make it positive 34. Sorry, negative 34 altogether. And we have that positive 34 down here that would cancel that out. So once again, we do see that the sum of the deviations is turning out to be 0, which again isn't really useful for us other than as a check. So we're going to need to go through and start squaring these to see what we get for them. And some of these I know, but some of them I don't. So let's go ahead and take the 22 and square that one. That'd be 484. Also square that 18, that's 324, and I think I can do the rest in my head. So let's see, for negative 22 squared we'd have 484. You might have noticed I didn't put the negative in the calculator. You always get the same answer when you square a number that has the same absolute value, whether they were negative or positive to begin with. The negative 11 squared is 121. Negative 1 squared is 1. 16 squared is 256. And the 18 squared, as we saw in the calculator, is 324. And according to the formula, and I'll write that down, we want to get sigma 2 here. We want the square root of the sum of the squared deviations divided by the number of data values. And I'm just going to extend this down because we want the square root of the whole thing. So I've just found all of the squares of the deviations here, and now I want the sum of that. So I'm just going to do that off to the side here on the calculator real quick. And I get 1186 for that sum. And so I'm going to want to plug that in here. Our sigma, our second sigma for data set 2 would be the square root of 1186, which is the sum of our squared deviations, divided by 5, which is the number of data values we had in this small population. And on the last example I did the division in one step and the square root in another, but typically I don't. If you do the division first, you're going to see the variance, and then you would take the square root and you would get the standard deviation. But in this class our focus is on the standard deviation, so I'm just going to do both those steps at once and say that I have the square root of 1186 divided by 5. And I'm going to round that using 5 digits altogether, so 15.401, so 15.401. And I'm going to go ahead and summarize the work that we've done here so far. We had our mean, median, mode from the previous page's work, and then we figured out our standard deviation for data set 1 on the previous page, and that was 7.5366. And now we figured out the standard deviation for data set 2 is 15.401. And we said that, if you look right back up here, we said data set 2 was more spread out, so we expected it to have a larger standard deviation. And now we see that is in fact what's happening. When you look at the two numbers there, you might think that it's a little inconsistent the way I did the rounding, and you would think that, I think, primarily if you were to focus on the number of decimal places, because I used 1, 2, 3, 4 here, but only 3 in this spot. When we do the standard deviation, this is a number that's going to be involved in a lot of multiplications and divisions. And when you're multiplying and dividing by a number, as far as accuracy goes, you're more concerned with how many total digits it has in it rather than just decimal places. And so I focused on that, and I did 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5 on this one as well. And that's the minimum that we're going to have for our rounding rule. So the rounding rule for standard deviations is to use at least 5 digits. You might also be familiar with the idea of digits in a different phrasing. If you took a class in science like chemistry or maybe physics, you would have heard these referred to as significant figures, or sig figs, sometimes they call them. So either way of referring to them is fine, but when we do a standard deviation, it's the total digits or significant figures that we want. It's not just about the decimal places. So I'm going to go ahead and show you just 3 quick examples of rounding with significant figures and then make a couple notes about that. Sometimes these can be a little bit tricky, so you might want to just pause the video for a second and try and round each of these 3 to what you would consider to be 5 significant figures, and then see if you get the same answer as I do. So go ahead and pause, try that, and then come back. Alright, so let me go ahead and show you what I did with these. This one's probably the easiest one. We want 5 digits altogether, so the 1, the 4, the 2, the 3, and the 0. So I'm going to write that this is approximately 14.230. Now, one of the things that's interesting about that is if I didn't write the 0, it'd still be the same number, but it would then only be written to 4 significant figures. And I want people to know that I really went out to the 5th one and it just happened to be a 0. If I leave that off, they don't know. Maybe it was 233 and I rounded it down. Maybe it was 228 and I rounded it up. So I want them to see, no, that was really a 0 in that spot. And then this one is kind of one of the most confusing ones, but it turns out that's not going to be a real big problem for us, the confusion. I'll explain that. If I rounded this to 5 digits, I'd have the 2 and the 1, 4, 5. Now there's 4 digits already, so the 5th one is going to be this 3. And that's going to be the last one I would write as a significant figure, and it'll stay 3 because it's followed by a 4. And then I still need placeholders though for everything from there to the decimal, so I'd put 0, 0. And I would consider that number to be 5 significant figures, 1, 2, 3, 4, 5. So when we have zeros at the end of a large number that are serving as placeholders till we get to the decimal place, those do not count in our list of significant figures. You can think of as an example to that, if you listen to the news and they say what the #1 movie at the box office was over the weekend, they'll often say something like the #1 movie brought in $75 million. And I would imagine you don't think like, wow, exactly $75 million, how could that have been right on the nose? We kind of assume they've rounded that. And that's common with big numbers, that people don't trust the zeros as actually being accurate. They just assume that they were rounded off. This isn't a real concern for us because if this was a standard deviation, I would have just gone ahead and written the 49 instead of 2 zeros, because it says here at least 5 digits. So I feel like if I'm going to write 7 things, I might as well write more accurate 7 things and go 7 digits instead of just 5. So on a big number like this, if you want to leave the original digits here instead of rounding them to zeros, that's totally fine, because the rule is at least 5, so more than that is okay. The thing that's tricky about part C is that the zeros at the beginning of a small number do not count either. And so when I start counting my digits, I wouldn't count any of those as significant. So the 2 is the first one, so the 2, the 3, the 7, and the 6. Now I've got 4 significant figures written down. I need 1 more, and so that would be the 2, but it's followed by a 9, so I'd round that up to a 3. And again, honestly, if it was a standard deviation and this is the number I got, I probably would have just kept the whole thing, because the rule is use at least 5 digits. And so if I wanted to use 6, that's not a problem. And the more you use, the more accurate it tends to be anyways. So this is the shortest answer you could put. This is the shortest you could put as far as the rounding. But if you want to put more, that would be okay. Just a quick note about this, by the way. If you were to put these in scientific notation, which we definitely don't need to do, but it kind of explains a little bit about what's going on there with what's important and what's not. This number could be expressed in scientific notation as 2.1453 times 10 to the 6th, and you wouldn't need to put those zeros in the scientific notation, and so you can kind of see like, oh, okay, we only need 5 of those. And if you did this one, it would be 2.3763 times 10 to the -3, and again you see when we went to scientific notation we didn't need those digits, just 1, 2, 3, 4, 5. So that gives you maybe a little bit of an insight as to why we wouldn't count the zeros at the end of a big number or at the beginning of a small one. But please don't be confused by this. You don't have to change these to scientific notation. This is the way I would leave all three of those if it was a standard deviation question. Okay, now that we've seen some examples of calculating the standard deviation for a population, I want to go ahead and show you how that's different if we're working with sample data. A random sample of 9 light bulbs was tested, and the bulbs were found to have the following lifetimes in hours. We wish to make estimates about all the variation in lifetimes for all such light bulbs. So we have our data set here, and they want us to find the appropriate mean and standard deviation. So it says the appropriate mean and standard deviation, and that word by itself doesn't tell you what type of mean and standard deviation it would be. But when we come back up here, we do see that they refer to this as a random sample. So the mean that we would be doing would be x bar, and the standard deviation we'll be doing is the sample standard deviation, and we'll learn the symbol for that in just a moment. So x bar, as we learned in section 3.1, is the sum of all the x values divided by the number of values that we have. So we want to make that computation. And all the data is right here. I want to go ahead and use the calculator to add those up. So let me go ahead and bring that in. So the first step would be to enter the data into my list editor. So I'm going to turn the calculator on. I'm going to press the stat key to get into the list, and I'll do that by choosing edit. I have some old data here, so I want to clear that out first. So I use the up arrow to highlight the list name, and then you'll see the list of numbers down here. When I press clear, that list goes blank even though they still stay here. It's just giving us kind of a safety that we don't clear data on accident. So we want to confirm that we want this to be an empty data set by pressing either down arrow, or what I'll do here is enter. Once we do the clear and enter, we get our blank list. So now I'm going to enter these numbers in. Alright, and once I have all those numbers in, I want the sum. And to do that, I'm going to have the calculator do that for me. I'm going to use this list to area as just some scratch work. So I'm going to use the right arrow just to be in one of the cells of L2. I don't have the list highlighted this time. And to get the sum, I want to go into the list menu, which is above the stat key. So I'll hit second and list. And I want to do some math here. So I'll arrow over to the math. And what I'm looking for is a sum. So going down to number 5. And down here it says that first entry in L2 is going to be the sum of something, and I want it to be the sum of L1. So I hit the second key and then L1, which is above the 1 key. So it looks like the sum of those is 6880.6. Sometimes there's digits you can't see, so it's a good idea to highlight it just to make sure there's nothing extra. In this case, that was the whole amount. Okay, so that's my sum. So 6,880.6. And the number of data values we have. They told us there was 9. We can also go over to our list and highlight the last one and see that it's saying that's the 9th one in the list. That's good confirmation of that as well. And then let's see what we get. So I'll go ahead and exit out of here to the regular home screen. 6880.6 divided by 9 items. And I get 764.5111 repeating. So I'll go ahead and round that. So I'll put the approximately equal symbol to let people know I brought in a little bit of error there. And I'll round that to a couple decimal places, which would be the minimum. Remember, our rounding rule for a mean is that we have to put at least 1 decimal place more than the original data. The original data had 1 decimal, so putting 2 is the shortest I can do. Alright, so now we're going to go ahead and calculate the standard deviation. And let me just go ahead and throw the formula down here for you, and then we'll work through it. So the symbol instead of sigma when we're working with the sample is we're going to use S. And the formula is almost the same as the one we had for population standard deviation. We're going to start off by putting a square root, and it's going to be of a fraction just like before. Our numerator before was the sum of x minus mu squared. Now because it's a sample mean, we're going to put x minus x bar squared. But that's essentially the same idea. The one thing that's a little bit different about this formula is instead of dividing by the number of pieces of data, which was capital N for a population, we're going to divide by 1 less than that when we do a sample standard deviation. So we're going to divide by n minus 1 in this situation. So it's very similar to what we did in the previous pages with population data. We want to subtract the mean from every data value. We want to square those differences. We want to add them up, divide, a little bit different number this time, and then take a square root. So let's go ahead and start seeing how that works. Alright, so we said we're going to do some differences, so let's go ahead and make a column for that. That'll be our x minus x bar part, so I'll put that right here. And then we can square those, which will be our next step. So this will be x minus x bar squared, and as we build these columns and finally find the sum here, we'll be getting the numerator of this fraction that we're working on. So we could go through and do these one by one. The first data value we have is already done. Let's go ahead and move to the second one. 660.6 is our x value, minus the mean that we just computed, 764.51. And we do that subtraction, we get negative 103.91. And then we just have to do that one more time. Down here we have another blank spot, so let's go ahead and fill that one in. So 876.8, and then also minus 764.51, and we get 112.29. And notice, just like before, that when your number is smaller than the mean, you get a negative deviation, and when it's bigger, you get a positive deviation. All right, and lucky for us, they had done a bunch of them, so I want to go ahead and show you a trick so that even if they haven't done them for us, we could still fill that in a little bit faster instead of having to go one number at a time. So if you go back into Stat and Edit, go over here to L2, let's go ahead and clear that out. And then if you highlight L2, it asks you what do you want L2 to be. When you have a repetitive calculation involving this list right here, which was L1, let me go ahead and label that. All right, we put our x values in L1. Then what is it that we're doing here? We're taking the x's, which are in L1, so I'll hit second L1, minus the mean, and the mean was, what was that, 764.51, I think. Let me have a quick double check. Yep. And if I press enter on that, it's going to fill L2 with all 9 of these differences. So when I do that, I can highlight them one at a time. There's the first one that was already filled in for me. There's the one that we did on our own. We can arrow down. There's our 112.29. One of the things that's supposed to happen with that list is supposed to add up to 0, so let's check that real quick using the list menu. Second, list, math, sum for the data that's in this list, which would be L2. That's supposed to be 0. Notice we get 0.01. The reason we're not getting a 0 there is because we didn't actually subtract the mean. We subtracted 764.51, but you might remember the mean was 764.511111 repeating. When you round your mean, that's no longer the perfect balancing point, so you'll get close to 0 instead of exactly 0. Now that trick is going to come in handy for doing this next column as well. Let's go ahead and label what we did on this column first of all. So we let L2 be the data that was in L1 minus 764.51, and we filled that in that way. We can do a very similar thing here. We can let this be L3 and just basically type the column heading that we have here. We have an open parentheses. We have the x's, which are in L1, minus the mean, which is 764.51. And then we want to square that. So let's go ahead and do that and see what we get for L3. So I highlight L3, and I want it to be open parentheses, L1 minus 764.51, end parentheses, and squared. And if I press enter there, I start getting the numbers that are shown here. So at first it doesn't seem like it's a match because this is 3920.0121 and I don't see that extra piece. But if you have it highlighted, you can see those extra 4 decimal places down here. So it is actually a match. And when I go to the second one, I can fill that in here now, 10797.2881. That's a pretty long number, but since the ones they already filled in have 4 decimals, I should be consistent and match that with the ones I'm doing now. So arrowing down, there's our 38294. Go down one more spot, that's the next one that's missing, 12609.0441. So I just filled in my deviations squared column. And what I want now is the sum of those deviations. So I'm just going to arrow over one spot, go to my list menu, do math. I want the sum, and that data is in L3, so second L3, and highlight it so I can see all the digits. And the sum is 164,545.0889. And so that number right there is the numerator I need when I compute S. So let's work on that. So what is S? S is equal to the square root of 164,545.0889 divided by 1 less than the sample size. So if this was a population set, we'd be dividing by 9 the number of pieces of data. Because it says n minus 1, we're going to be dividing by 8. That sample size, which was 9, minus the 1. And then we're going to put this into our calculator and get our sample standard deviation. So let's go to the home screen where we have a little bit more room to work. Okay, so we want the square root of 164,545.0889 divided by 1 less than the sample size, which is 8. When we end those parentheses, make sure that we're doing that with both numbers inside, so we're taking the square root of the whole thing. And when we do that, we get 143.4159549. We don't need all those digits. Our rounding rule says that we should put at least 5 digits. That's counting before and after. So that would be 143.42. And if I move that piece of paper, there it is. So that's how we calculate our sample standard deviation. All right, now let's take a quick look at how we can use the sample mean and standard deviation that we've calculated. Let's do that by moving on to question B. If you bought 23 of these light bulbs to use one after the other in the same lamp, then how many total hours of lifetime should you expect? Well, if you had 23 light bulbs, then they should last on average about 764.51 hours each. So what I'm going to want to do to get the total lifetime is take the 23 light bulbs and multiply that by the average that I expect for light bulbs, which would be 764.51. And when I take that average times the number of light bulbs that I'm going to get, that'll give me an expected total. So let's go ahead and bring the calculator in real quick and see what we get. 23 times 764.51 gives 17583.73, and that would be the total number of hours that we'd expect for those light bulbs. And it is important to point out that's how many we expect to get, not necessarily how many we will get. This mean just came from a sample, so it's an estimate of the population mean, which is itself an estimate of what future sample means would be. So what we got from these 9 gives us a decent guess at what we'd get for a future 23, and multiplying that by 23 gives us a reasonable expectation for the total. All right, now let's look at this next question. What percentage of the data lies within one standard deviation of the mean? So this is going to be an important question to us as we get to later sections, so let's go ahead and take a look at how that works. Okay, so they want to know what percentage of the data lies within one standard deviation of the mean. So there's a couple different ways to do this, but when you have just made a table, I think the easiest way to answer this question is to just look at the deviations themselves in the list. This tells you how far away from the mean each of these data values was. So the 701.9 was 62.6 units, 62.61 units away from the mean. And the standard deviation was 143.42, so apparently that distance away was less than one standard deviation worth of distance. So I'm going to mark that one with a star. The next data value, 660.6, was 103 away from the mean, and that's smaller than 143. And so I just keep doing that, looking at these deviations to see are they smaller or larger than the 143. Here's another one that's smaller, another one that's smaller. But when I get to this light bulb that lasted 960.2 hours, that was 195.69 hours above the mean. That's more than one standard deviation above the mean, so I'm not going to count that one. This 960 is not within one standard deviation. 112 for the next deviation is smaller than the standard deviation, so I count that. So is the 55. And just barely the 148.99 is just a little bigger than one standard deviation. So this light bulb that lasted 913.5 hours, I'm not going to count. And I'm not going to count the one for 511.2 hours either, because this one was below the mean, but it was 253 below the mean. That's more than one standard deviation away. So notice that I didn't really worry about whether the deviations were negative or positive. That just tells me whether these initial x values were to the left or the right of the mean. When I'm thinking about distance, I'm going to ignore those negatives, just think absolute value, and then with the absolute value size smaller or larger than 143.42. And I marked each one. We can count them up. There's 1, 2, 3, 4, 5, 6 of them, and that's out of 9. So we have 6 out of 9, which we can go to the calculator on to get a decimal. I happen to know that one, so I'll just write it down. It's 0.6667, and then changing that to a percentage, that would be 66.67%. And so that's what percentage of the data lied within one standard deviation of the mean. If they change that question to what percentage of the data lies within 2 standard deviations of the mean, we just have to make a small change before we do a similar task, and that would be take that value of s and multiply it by 2 and see how big that is. So I'm going to take 2 times 143.42 and see what I get for that. So let's see, 2 times 143.42 is 286.84. That's 2 standard deviations distance from the mean. So now I want to see, are any of my data values more than that far away, or are they all closer? So of course all the ones that were less than 1 standard deviation away are less than 2, so I just want to double check the other ones and see if any of them still fall outside. So let's see, the 195.69 is a deviation. That is smaller than our 2 standard deviation multiplier, so now I'm going to all of a sudden be counting that one. I'll go ahead and just put the star on the other side so I can see the difference. 148 is definitely smaller than 286. And even our data value that was furthest away from the mean at 253.31 hours below the mean, that's still less than 2 standard deviations, so now that one's getting counted as well. So now that you look at our chart, looking at the 2 standard deviation, we had the 6 we had before, we picked up the other 3, and we've got all 9 out of 9. And we don't need our calculator for that one. 9 over 9 is 1, which is 100% of the data that lies within 2 standard deviations of the mean. We'll keep looking at questions like that in future sections and in the homework, and later on we'll see that there's a pattern to what kind of answers you typically get for these questions. Alright, so here's a quick summary of what we learned about sample standard deviation. The sample standard deviation formula is the square root of the sum of the squares of the deviations from the mean divided by the sample size minus 1. And the variance is the square of the standard deviation, so if you squared both sides, the square root would go away, so our variance s squared is the sum of the squared deviations divided by n minus 1 without the square root, where n is the size of the sample. And the one difference that really showed up in this formula mechanically that was different from population was that dividing by 1 less than the sample size instead of dividing by the actual number of data values. So, quick question about why is that? So, why do we divide by n minus 1 rather than just dividing by n? And the answer to that question is that the purpose of finding the sample standard deviation is to estimate the population standard deviation. And samples tend to have less dispersion than the populations they're drawn from. And when we use that n minus 1, it decreases the size of the denominator and thus increases the size of the sample standard deviation. And that makes it a better estimate for the population standard deviation. So deep down, the answer to why do we use n minus 1 instead of n is a calculus thing. But this is just giving a quick kind of justification for why it makes sense. It's saying samples tend to have less dispersion, so if we calculated the standard deviation in the same fashion as before, our answer would be a little bit too small as an estimate for what's happening in the population. So when we decrease the size of that denominator, it increases the size of the answer in an amount that makes it a better estimate. Why is that the perfect adjustment? That is a calculus thing. But this is the adjustment that works. It's simple to do mechanically, and we just have to remember it is different for samples and populations. And then just a quick reminder, I showed you some tips on how you could speed up the column use of the calculator. to make this table fill in kind of all at once instead of one calculation at a time. And that can be handy when your data sets get a little bit bigger, so keep that in mind as you're doing the homework. And if you see Appendix A and B of the text, you can see some help for how to do it on the calculator with the TI 83, 84, or in Appendix B, the Casio. All right, that wraps up section 3.3.